Welcome to the deep dive. We're not just skimming the surface, we're plunging into the heart of fascinating topics to bring you the core knowledge you need.
Hmm.
Today we're tackling something truly revolutionary, Einstein's mathematical theory of relativity.
Big topic.
Huge. We've got a collection of scientific papers that, laid the groundwork for this mind-bending view of the universe.
Right.
And our mission is to extract the key insights and make this complex subject not just understandable, but, well, genuinely captivating for you.
It's quite an adventure we're setting off on, intellectually speaking. And what's striking right from the get-go is that the author, well, in pulling these original papers together into one story,
Yeah.
they had to make some pretty significant adjustments. And that tells us something really crucial, I think,
What's that?
that even our most, fundamental scientific theories aren't just handed down perfectly formed. They're built, they're refined, sometimes reinterpreted.
Like a work in progress.
Exactly. The author even flags up a different take on the principle of stationary action. Just reminds us that even the bedrock principles can have different viewpoints.
Okay, let's unpack that. So, the very start of this deep dive is grounded in this idea that science is, well, dynamic, a constant evolution of understanding,
Mm-hmm.
a process. And in this exploration, we'll be zoning in on some really fundamental shifts, changes in perspective from relativity,
Right.
how we think about space and time itself.
The fabric of reality.
Yeah, how we measure things in this new picture, Einstein's completely different take on gravity,
Revolutionary.
and how light and matter behave under these new rules. So get ready for some genuinely surprising twists and ideas that will probably challenge your assumptions about the universe.
Absolutely. Let's start with something that might seem totally basic.
Mhm.
What physical quantities even are, and how we actually measure them.
Okay.
The source material makes this really profound point, that the physical quantities we use, they aren't just passively observed. They are, in a way, manufactured by what we do to measure them.
Manufactured. How so?
Well, think about it. Distance isn't just out there. It's what we figure out by, say, laying down rulers or using lasers.
Right, the act of measuring defines it.
Precisely. Or the parallax of a star. You know, how it seems to shift against the background as Earth moves.
Yeah.
That's not really a property of the star itself, is it? It's a result of our specific observations, our calculations. These quantities are products of how we interact with the world.
Huh. That's a bit of a head scratcher. We tend to think of distance, things like that, as just
Inherent.
fundamental.
We do.
But the author throws this curveball, suggesting that even something that seems arbitrary, like cubic parallax, just cubing the measured parallax,
Yeah.
that has the same kind of operational reality. It's a number we can define and calculate from our measurements.
Exactly. So that line we draw between what feels fundamental and what feels derived. Well, maybe it's more about our habits of thought than some deep truth about the universe. It is. And physics progresses, right?
Yeah.
By replacing these quantities defined by specific measurements with more fundamental theoretical concepts.
Like what? Any examples?
Well, remember the old idea of vis viva? It was basically a measure of an object's ability to do work, measured pretty directly.
Vaguely.
That evolved into the much more abstract, much broader concept of generalized energy, defined by its conservation property.
Ah, okay.
So sometimes science flips the problem around. Instead of just finding properties of things we see, we start with a theory that assigns properties, and then we look for something in nature that fits.
So we build the framework first, then see if reality matches.
In a way, yes.
Yeah.
It's powerful.
Yeah.
But the source wisely warns us, you have to be careful when you're reconstructing theories. What if nature doesn't quite play ball with the properties we assigned?
Right, you might force it into a box that doesn't fit. So we need to stay vigilant. Now, the text also talks about two ways to describe events, using coordinates or using mutual intervals between them. What's the key difference there? Why does it matter?
Well, coordinates are, concise, efficient, like addresses for events in space and time.
Okay.
But their meaning is totally tied to the specific coordinate system you choose, the relative.
Got it. And intervals.
Intervals, specifically the space-time interval we'll get into, they have an absolute significance. They are invariant, meaning their value stays the same, no matter how the observer is moving or what coordinate system they're using.
Okay, that sounds fundamental.
It is. And to connect these to the relative coordinates and the absolute intervals, we need a fundamental mathematical relationship. In relativity, that turns out to be a quadratic form.
Okay, quadratic form. Sounds a bit technical. Can you break that down a little?
Sure. It's just a type of math expression with squared terms. Think of it like a formula for calculating a kind of distance, but not just in space and time together.
Right, space-time.
Exactly. And for flat spacetime, this fundamental quadratic form is the Minkowski metric. ds squared equals dx squared plus d squared plus dz squared minus c squared dt squared.
Ah, the famous one.
That's the one. It gives you the fundamental distance, the space-time interval d squared, between two events based on their separation in space, dx, d-day, dz, and time, dt. And crucially, there's c, the speed of light, acting as the conversion factor.
The glue between space and time.
You could say that. The source also briefly explains why you can't really use a more complicated form that mixes space and time terms differently, especially when you consider events separated in both space and time for different observers.
Okay, so this Minkowski metric is foundational, a tool for describing events that respects this deep link between space and time. Now let's shift to the relativity of motion and the speed of light. The Lorentz transformation gets mentioned. What is that and why is it such a cornerstone?
Right, the Lorentz transformation. It's basically a set of equations.
Yeah.
They tell you how measurements of space and time coordinates change when you switch between two inertial frames of reference.
So two observers moving at constant velocity relative to each other.
Exactly. And what's really remarkable, the key property, is that this transformation leaves that Minkowski metric, the E stays squared, completely unchanged.
So even if the observers disagree on the space distance or the time difference.
They both calculate the exact same value for the fundamental space-time interval between those events. It's invariant.
Wow. And the U in the equations.
That's just the relative velocity between the two frames.
Yeah.
And, it's a neat algebraic point. It shows the symmetry.
Mm-hmm.
If S moves at velocity U relative to S, then S moves at U relative to S.
Relative velocity is relative. Makes sense.
It does.
Now, the source also dives into the uniformity of the speed of light. It says, this idea that light speed is the same in all directions for everyone, no matter how they're moving, isn't just an observation. It's a deduction based on a hypothesis and how we keep time.
You've hit a really crucial point there. The constancy of light speed isn't purely from experiments. It's deeply tangled up with how we define time and the basic assumptions, the postulates of relativity.
How so?
Well, the source explains that our convention for synchronizing clocks far apart, imagining moving a clock super slowly between them.
Yeah.
That method turns out to be mathematically equivalent to just assuming that the speed of light going one way is the same as its speed coming back.
Ah, so it's partly built into the definitions we use. What about the Michelson-Morley experiment, then? Isn't that the big proof?
It's often presented that way, but the source gives it a slightly different role. Less as the sole inductive proof, and more as something that helps solidify the link between how light actually travels and that fundamental speed seizing in the Minkowski metric. It kind of filled a gap in a largely deductive argument.
That's a really interesting perspective. It wasn't just about what it found or didn't find, but how it slotted into the bigger theoretical picture. The text also mentions Fizeau's experiment. What did that add?
Fizeau's experiment, back in the mid-1800s, was ingenious. It measured the speed of light through moving water.
Right.
And it gave independent evidence that this fundamental speed c that we're talking about is indeed very, very close to the measured speed of light. Later, Zeeman did even more precise versions, an even closer match, showing any possible difference between the fundamental velocity c and light speed is incredibly tiny, less than like 1 part in 500.
So multiple lines of evidence, theory, and experiment, all pointing to this universal speed limit, which is the speed of light.
Converging, yes.
Okay. Now let's move to space-time intervals and this dramatic-sounding thing called the null cone.
Yeah, it does sound dramatic. The space-time interval in these odds lets us categorize the relationship between any two events. The source gives the equation, ds dt, squared equals c squared minus v squared.
Where v is the relative velocity.
Right. Now, if v is less than c, the speed of light, the d sign is positive. That's a time-like interval.
Things that can be causally connected, like us experiencing time.
Exactly. That's our direct experience. But if I were somehow greater than c, which relativity says isn't possible for information, then d squared becomes negative. That's a space-like interval. Events too far apart in space to affect each other in the time available.
Okay. Time-like, space-like. Where does the null cone come in?
The null cone is the boundary case. D squared equals 0. This happens when events are separated exactly by the speed of light, so v equals c.
Ah, the light speed limit again?
Precisely. Picture any event as the tip of a double cone stretching through space-time. The surface of that cone represents all the possible paths for light rays coming from or going to that event.
So light travels on the cone?
Exactly. Events inside the cone have a time-like separation from the tip they're in the causal past or future. Events outside have a space-like separation causally disconnected.
And this holds even in curved space-time.
The concept does, yes. Instead of a perfect cone, you get a more complex null surface, but it still marks that boundary for light-speed connections. It's the causal structure of the universe, defined by C.
It's like a cosmic speed limit map. Powerful image. Okay, let's talk about something we all feel. Time. How does relativity fundamentally change how we understand time itself?
This is really pivotal. The source stresses that time, in physics and astronomy, is actually quite sophisticated. It's different from our basic, primitive sense of time passing.
How so?
Our immediate awareness of time is really tied to those time-like intervals along our own path through the world. We feel a sequence of events along our personal track.
Our own timeline.
Right. But trying to mesh together these personal time sequences from different observers, different clocks, into one universal now, that needs much more careful thought than pre-relativity physics gave it.
Because clocks and our time sense measure the interval.
Exactly. They measure the interval along their own world lines. So the problem really becomes, how do we get from these personal intervals to a more objective description using coordinates?
So our subjective time is local, tied to our journey. But what about simultaneity? Events happening at the same instant. Relativity famously says that's not absolute.
Exactly. The Lorentz transformations show this beautifully. What's simultaneous for me might not be simultaneous for you if we're moving relative to each other.
How does that work mathematically?
The source gives an expression. dt equals minus beta u dx prime over c squared. That dt is the time difference observer S measures between two events that are simultaneous for observer S prime, so dt prime is 0, and are separated by dx prime in S prime's frame.
And why does this difference arise?
Fundamentally, it comes back to how we define simultaneity, that idea of slowly transporting clocks. What counts as infinitesimally slow turns out to be relative. Depends on your motion. And that difference leads directly to disagreements about what's simultaneous.
The text even walks through a thought experiment. Light signals between 2 points, A and B, in relative motion.
Yes, that's a classic illustration.
What's the main takeaway from that?
The key insight is that it vividly shows how the different relative speeds of the clocks, as seen by each observer, lead them to calculate different arrival times for light signals. Observer S calculates a later arrival time at B than S expects, even after accounting for things like Fitzgerald contraction.
So length contraction.
Right. This disagreement about simultaneity isn't a mistake. It's a direct, unavoidable consequence of the core principles: constant light speed, relativity of motion. It really hammers home that our everyday intuition of a single, universal now just doesn't hold up in relativity.
It really does challenge our basic intuitions. Okay, let's shift to other core concepts. Mass, momentum, energy. How does relativity view these?
Well, the source points out, if you stick with the old Newtonian definition of momentum, mass times velocity, mgx dt,
Yeah.
then a general conservation law only works across different observers if you let the mass m actually change with velocity.
But relativity offers a different approach.
It does. A slightly modified definition. Momentum is m dx ds. Here m is an invariant quantity, the proper mass. And ds is the space-time interval.
And with that definition,
The conservation of momentum law holds true for all observers in all inertial frames simultaneously.
okay, so this proper mass, that's like the object's intrinsic mass, the mass it has when it's at rest, which doesn't change.
Exactly. And if you compare this relativistic momentum with the classical one, you derive that famous equation for relativistic mass. M. M equals m divided by the square root of 1 minus v squared over c squared, or m times gamma, the Lorentz factor.
Right, so the observed mass increases with velocity, v.
It does. By the same factor involved in Fitzgerald length contraction, when v is 0, m just equals m, the proper mass.
And this is where E's energy comes from, isn't it? The mass-energy equivalence.
Precisely. If you extend momentum to a 4-component vector, 3 space parts, one time part related to energy, you see this beautiful symmetry. Momentum is the space part, mass or energy is the time part.
A 4-vector.
Yes, and the conservation laws become about conserving this whole 4-vector. Then if you look at the relativistic mass equation at low speeds, much less than c,
Yeah.
you can do a mathematical approximation And it shows the increase in mass corresponds exactly to the kinetic energy, the half mv squared term.
So E is approximately mc squared plus a half mv squared.
Right, which strongly suggests mass and energy are equivalent. And the proper mass m is interpreted as the internal energy of the body at rest, leading to the full EMC math for the total energy.
It's crucial, though, as the source says, to distinguish invariant proper mass m from the relative mass m.
Very important. We often treat m as constant for an object, but conserving m isn't the same as the universal conservation of energy, which includes mass energy related to m. Think electrons versus billiard balls. M is fundamental in their West frame.
Okay. Moving on, the source touches on how relativity affects other things, like density and temperature.
Right. Particle density, just number per unit volume. Sigma, not invariant. Because of Lorentz contraction. Volume V shrinks for a moving observer. So the observed density sigma prime will be higher than the rest frame density sigma. It's sigma prime equals sigma times beta, that Lorentz factor again.
Makes sense. Volume contracts, density goes up. What about temperature? That feels pretty fundamental.
Well, interestingly, entropy ds equals dm over T. A measure of disorder is considered invariant in relativity.
Okay.
And because energy mass, dm, transforms with motion, and entropy ds doesn't, then temperature T must transform to keep the equation balanced.
How does it transform?
It leads to T prime equals beta times T. So a moving observer sees a higher temperature. This would affect thermodynamic equations, like for gases, if you applied the full relativistic treatment.
Wow, so relativity reaches into thermodynamics too. Okay, let's connect coordinates and the gravitational field. This is where things get really dramatic with Einstein.
Yes, coordinate systems where you can write the interval in that simple Minkowski form.
ds squared, ESDS squared, etc., plus c squared dt squared.
Exactly. Those have a very direct link to what our scales and clocks actually read. But the crucial point, only Lorentz transformations keep that simple form.
So if you use other coordinate systems,
More general transformation, maybe to describe rotation or acceleration, you lose that direct physical interpretation. The source even warns against trying to, quote, improve transformations to rotating axes. It often just hides complexity that leads you back to something like the original inertial frames anyway.
Okay, so sticking close to those natural inertial-like coordinates is key for linking math and measurement. But what happens when space-time isn't flat? When gravity enters the picture, the text talks about a mistaken observer.
Right. Imagine someone who thinks they're in flat space-time, Minkowski space, but they're actually in a curved geometry because of mass and energy nearby.
Okay.
Since you can, in principle, measure space-time intervals experimentally timing light beams, for instance, this observer would eventually find that their predictions based on flat space don't match reality.
They'd see discrepancies.
Exactly. But instead of questioning their basic assumption about the geometry, they might invent some external influence, some force, to explain why things aren't moving in straight lines at constant speed like they should in flat space.
And that invented force.
That hypothetical supernatural agency they cook up to explain deviations from straight-line motion. That's precisely what we traditionally call a field of force, like Newtonian gravity.
So gravity, the force we think of pulling things, could just be us fundamentally misinterpreting the geometry of the universe.
That is the absolute core insight of general relativity, a revolutionary idea.
It really is.
The source argues that with gravity, it's inherently impossible to find one single coordinate system covering everything that perfectly matches our old ideas of ideal rectangular coordinates and universal time.
Why not?
We usually blame this failure on the gravitational field. But that field, the Newtonian one, depends on our coordinates. And crucially, you find you can't get rid of its effects everywhere just by switching coordinates. There's always something left over.
An irreducible field of force.
Exactly. And that irreducible part, and what Einstein identified as gravitation, it's not a definite force field in space, like Newton thought. It's the inherent irreducibility, which is a manifestation of the underlying curved geometry of space-time itself.
So gravity isn't a force in space, it's the curvature of space-time.
Beautifully put. The irreducibility is equivalent to the geometrical properties.
Wow. Okay, to describe this curvature mathematically, we need tensors. The text introduces contravariant and covariant vectors. What are they? Why the distinction?
Right, tensors. When we change coordinates, switch how we label points, contravariant and covariant vectors are just types of mathematical objects whose components change in very specific, consistent ways.
How specific?
A contravariant vector, usually written with an upper index like AMU, transforms using derivatives of the new coordinates with respect to the old ones. A prime mu equals partial x prime mu by partial x alpha times a alpha.
Okay, and covariant.
Covariant vectors, lower index like a mu, use derivatives of the old coordinates with respect to the new ones. A prime mu equals partial x alpha by partial x prime mu times a alpha.
Why do we need two different rules? What's the point?
These different rules are absolutely vital for ensuring our math descriptions are self-consistent. Think about velocity. If you rotate your axis, the number of components change, right?
Sure.
But the actual physical velocity hasn't changed. These transformation rules guarantee that our mathematical objects, the vectors, transform in just the right way to reflect that underlying physical reality, making sure our physical laws stay valid no matter the coordinate system.
So they keep the physics consistent across different perspectives.
Exactly. The source even says these are basically the only mathematically consistent ways numbers can transform between coordinate systems, apart from maybe multiplying by powers of the Jacobian, which relates to tensor densities later.
Okay. So tensors give us a language to write physical laws that are fundamentally independent of the observer or coordinates. The text also mentions the physical notion of a vector.
Yeah, contrasting it with the pure math definition. Mathematically, a vector is just components transforming by the rule.
But physically,
When we talk about force, say, we picture an underlying condition in the world, existing independently of how we write its components down. The transformation rules are designed precisely so the math vector accurately reflects that coordinate-independent physical reality.
and this extends beyond vectors to higher rank tensors, more indices.
Yes, they're generalizations, and the guiding principle is, in any equation for a physical law, both sides must have the same elements of covariance and contravariance. It's like a generalized dimensional analysis.
Ensuring consistency.
Exactly. Covariance and contravariance are like a generalized directionality, showing how the measure of one thing changes when we change the measure of another. Even changing units, meters to feet, is just a simple case of this broader framework.
Coordinates themselves are just labels.
Just identification numbers. Changing coordinates is mathematically on par with any other change in how we measure things.
The text mentions the Jacobian and the rigorous quotient theorem. What's their significance?
The Jacobian is a determinant that pops up in transforming tensor densities. It measures how volume scales between coordinate systems.
And the quotient theorem.
That's a really useful shortcut. It helps you figure out if something is a tensor. Basically, if you combine your unknown quantity with an arbitrary known tensor, and the result is always another predictable tensor, then your original quantity must have been a tensor too.
Save checking all the transformation rules directly.
Exactly.
And finally here, the fundamental tensor G mu nu. The metric tensor. How's it derived? Why so fundamental?
The metric tensor, G mu nu, is intrinsically tied to the invariant spacetime interval, dc squared. The relationship is d squared equals G mu nu times dx mu times dx nu.
Summing over the indices.
Right, Einstein's summation. Now, since d squared is an invariant, a scalar, a rank 0 tensor, and dx mu is an arbitrary contravariant vector, an infinitesimal displacement, that quotient theorem we just mentioned tells us that q mu nu must be a covariant tensor of the second rank.
Okay.
And it's fundamental because it encodes all the information about the geometry of space-time in a given coordinate system. How to calculate distances, angles, volumes. It appears everywhere. It's the foundation relativity is built on.
Okay, so G mu nu defines the geometry. Now, how do we take derivatives of tensors in curved spacetime? Normal calculus derivatives won't work, right? That's where covariant differentiation comes in.
Absolutely correct.
Yeah.
In curved spacetime, just taking a partial derivative of a tensor generally doesn't give you another tensor.
Why not?
Because the coordinate basis vectors themselves change from point to point in curved space. To fix this, we need a generalized derivative that accounts for this changing basis and ensures the result is a tensor. That's covariant differentiation.
And it involves Christoffel symbols? They sound a bit intimidating.
They can seem that way. The Christoffel symbols mu, nu, sigma basically capture how those basis vectors change as you move infinitesimally in curved spacetime.
Are they tensors themselves?
No, they're not. But they're derived directly from the metric tensor G mu nu and its first derivatives. By including them in the derivative definition, we compensate for the changing basis and ensure the result transforms correctly.
So there are specific formulas.
Yes. For a covariant vector amu, the covariant derivative amu nu is the partial derivative minus a term with the Christoffel symbol and a alpha. Similar formulas exist for contravariant vectors and higher-rank tensors, all using these symbols.
So the covariant derivative is the right tool for rates of change in curved spacetime, keeping everything tensorial and physically meaningful. The text mentions a distributive rule, like in normal calculus.
Yes, that holds. The covariant derivative of a product, b times c, is derivative of b times c plus b times derivative of c.
Yeah.
Very useful.
And also that the covariant derivative of the metric tensor itself is 0. G mu nu sigma, ER0.
Crucial result. It might seem technical, but it means the metric is constant regarding covariant differentiation. This lets us raise and lower indices on tensors, even within covariant derivatives, without messing up their tensorial nature or physical meaning.
Now, the principle of equivalence comes up again here, linked to covariant differentiation. How do they connect?
The principle of equivalence suggests that physical laws, written tensorially in flat spacetime, special relativity, should keep that same general tensor form in any spacetime, even curved ones with gravity.
And covariant derivatives let us do that.
Exactly. They provide the mathematical machinery. You take a law with ordinary derivatives in flat space, replace them with covariant derivatives, and voila, you have a generally covariant equation, expressed entirely in tensors.
Which should then hold in curved spacetime, too.
That's the idea. Because tensors transform consistently, the new law should hold in any coordinate system, any geometry. But, as the source rightly notes, this is a big leap. It needs experimental verification.
Makes sense. Just because it works in the simple flat case doesn't guarantee it universally. But it's a powerful guide. The source says the physical rate of change is represented by the covariant derivative. Why is that important?
Well, many fundamental laws involve rates of change, Newton's second law. Force is rate of change of momentum, right?
Right.
To make these laws universal, independent of observer or coordinates, the rates of change need to be tensors. The covariant derivative is that tensorial rate of change.
And it matches the old way in simple cases.
Perfectly. In flat spacetime, with simple coordinates, the Christoffel symbols vanish, and the covariant derivative just becomes the ordinary partial derivative. So it smoothly connects general relativity back to classical physics where it applies.
Okay, so covariant differentiation lets us extend physics from flat to curved spacetime. Now let's tackle curvature itself and the Riemann-Christoffel tensor. Sounds formidable.
It does, doesn't it?
Yeah.
In flat space, the order you take derivatives doesn't matter. Second derivative respect to x then y is the same as y then x.
Right. Commutative.
But in curved spacetime, the order of covariant differentiation does matter. They don't commute. And this non-commutativity is a direct measure of the curvature.
How is it measured?
By the Riemann-Christoffel tensor, b epsilon mu sigma nu, or sometimes r. The difference you get from differentiating a vector I mu twice in different orders, nu then sigma versus sigma then nu, is directly proportional to this Riemann tensor acting on the original vector.
So the Riemann tensor is the mathematical measure of spacetime curvature at a point.
Precisely. It tells you rigorously how much the geometry deviates from being flat. It also has important symmetries. And by mathematically contracting it, summing over certain index pairs, you get other curvature tensors, like the Ricci tensor G mu nu. And contracting that further with the metric gives the scalar curvature, G, just a single number representing the overall curvature at a point.
And what's the condition for spacetime to be truly flat using this tensor?
Simple. The Riemann-Christoffel tensor must be 0 everywhere in that region. If it is, you can always find natural coordinates where the metric tensor G mu nu is constant, like the Minkowski metric.
But if it's not flat?
If Riemann is non-zero, you can't find a global flat system. But around any specific point, you can find canonical coordinates where the first derivatives of G mu nu vanish. The spacetime locally kisses or osculates with a flat space. And the second derivatives in these coordinates are directly related to the Riemann tensor components there.
So Riemann encapsulates curvature, and curvature is gravity in Einstein's view. How do we get the law of gravitation itself from this geometry?
Einstein's field equations. They are the heart of it. For empty space, no matter or energy, the equations are beautifully simple. G mu nu equals 0.
The Ricci tensor is 0.
Yes. The source then discusses finding a specific solution to these vacuum equations that matches the gravity field of an isolated, spherical, non-rotating stationary particle. That search leads directly to the famous Schwarzschild metric.
The Schwarzschild metric. Heard of it. What does it describe exactly?
It's a specific mathematical solution to G mu nu E00. It describes the geometry of spacetime outside a non-rotating spherically symmetric mass. It's usually written in spherical coordinates r theta phi up t.
And the form is?
D squared equals 1 to millar, inverse tau squared, d theta squared, r squared sin squared, theta d phi squared plus 1 2 millar bt squared.
Okay. R is radius, T is time. What's M?
M is a constant directly related to the mass of the object. The source probably details the calculation finding Christoffel symbols for a general spherical static metric, plugging into G-minu 0, and solving to find the metric components depend on R as 1 2 millar.
And that 2 millar R term seems key. What's its significance?
It's crucial. M is proportional to the mass, gmc squared. So 2 millar represents the strength of gravity at radius R. When R is huge compared to M, weak field, far away, the term is tiny, and the metric look like flat Minkowski space.
But close to the mass.
As R gets smaller, 2 millar R gets bigger, space-time curvature increases, and famously, the metric shows a singularity at R each 2 meter.
The Schwarzschild radius, the event horizon.
Exactly. Anything crossing that radius can't get back out. But importantly, the source also notes that in weak fields and low speeds, Schwarzschild predictions reduce back to Newton's gravity law. Einstein extends Newton, doesn't just replace him everywhere.
Okay. The text then mentions some groundbreaking predictions from the Schwarzschild metric, like Mercury's perihelion precession.
Yes, that was a huge puzzle. Mercury's orbit shifts slightly more than Newtonian gravity, considering other planets, could explain.
And general relativity.
Using the Schwarzschild metric to calculate planetary motion, GR predicts a tiny extra precession for Mercury each orbit, and the predicted value matches the observed anomaly remarkably well. One of the first big confirmations.
Amazing. And the bending of light near the sun, another famous one.
Right. By looking at light paths in Schwarzschild geometry, remembering light follows null geodesics dsc squared equals 0.
Yeah.
GR predicts light rays will bend as they pass through a gravity field. It makes a specific prediction for the deflection angle of starlight grazing the sun.
Which was tested during eclipses.
Famously, yes, measuring star positions near the eclipsed sun. The observed deflection matched Einstein's prediction very accurately. More strong support.
And finally, gravitational redshift. What's that?
That's light changing frequency, or color, as it moves through a gravitational potential. Because the time component, GTT, in the Schwarzschild metric depends on gravity.
Clocks run differently.
Exactly. A clock deeper into gravity, well, ticks slower, as seen from outside. So light climbing out of gravity loses energy. Its frequency drops. It shifts towards red. Light falling in gets blue shifted. The shift depends on the potential difference.
These are all dramatic, non-Newtonian predictions, verified experimentally. Really builds confidence in GR. Now, the text mentions isotropic coordinates. How do they relate to Schwarzschild?
Isotropic coordinates, R1, theta, phi, are just another way to write the same underlying Schwarzschild geometry using a different radial coordinate, R1. The metric looks different mathematically.
But D-line describes the same physics.
Exactly. One advantage is that in isotropic coordinates, the calculated speed of light at a given radius r1 is the same in all directions, not obvious in standard Schwarzschild coordinates.
Are these isotropic coordinates closer to how we measure things on Earth?
In a way, yes. The coordinate length of a rigid rod doesn't change with orientation in isotropic coordinates. That feels more like how we use rulers or triangulation.
So maybe more operational.
Perhaps. But remember, here on Earth, gravity is incredibly weak. Mr. is tiny. In that limit, both Schwarzschild and isotropic coordinates basically look like flat Euclidean space anyway. The weirdness only really shows up in strong fields or very precise measurements.
The source then makes an intriguing point. Schwarzschild and isotropic forms are just two examples from an infinite series of solutions made by substituting arbitrary functions of R. Why is that possible?
It comes down to a mathematical quirk of the Einstein equations for a static spherical vacuum. There's an identical relationship between some Ricci tensor components, G11, G22, G44, meaning when you set the Ricci tensor to 0, G mu nu equals 0, you effectively only have two independent equations to determine the three unknown functions defining the general metric. That leaves one degree of freedom.
Which allows this arbitrary function of R.
Exactly, leading to this infinite family of mathematically valid solutions. It also hints at something deeper. Because we can transform coordinates freely, there must be identical relations among the 10 Ricci tensor components themselves. That's explored later.
It really underlines that coordinate independence. Physics doesn't care how we label points. Okay, the text shifts to other gravitational effects beyond Mercury and light bending.
Yes, GR's effects extend subtly elsewhere. The sun's gravity, described by Einstein, isn't quite Newtonian. This leads to tiny corrections in how the sun perturbs the moon's orbit.
And interactions.
GR predicts cross terms between the sun's and Earth's fields. The combined field isn't just a simple sum. Nonlinearity matters.
What about the moon's orbit around Earth itself? Any relativistic effects?
Earth's gravity, like the Sun's, has relativistic modifications. In principle, this should cause a tiny precession of the Moon's perigee, the closest point to Earth, analogous to Mercury's perihelion shift.
But is it detectable?
The source says the predicted effect is extremely small, likely too small to easily measure with technology at the time.
The text introduces perturbing forces, R and phi, added by GR to classical dynamics. What are they?
They represent exactly those extra gravitational influences from the relativistic corrections. Derived from the metric tensor components and their derivatives, they depend on velocities and the central mass. They're what cause the deviations from Newton, like perihelion shifts.
The Moon's perigee advance is mentioned again, 1.94 arcseconds per century. How does that compare to observations or de Sitter's calculations?
The GR calculation agrees reasonably well with de Sitter's value. Slight differences noted. However, the actual observed irregular fluctuations in the Moon's position are much larger and blamed on other complex factors, like tides, other planets.
But what's the interpretation of that 1.94 arcseconds?
Interestingly, it's seen not just about the Moon, but as a tiny precession of the local inertial frame near Earth relative to distant stars, a property of the warped spacetime around Earth.
Meaning our local sense of direction or non-rotation is slightly dragged?
Yes, implying a tiny difference between Earth's rotation measured against stars versus locally, like with a Foucault pendulum, though, again, extremely small.
Wow. Even inertia is subtly tied to the cosmos. Okay, let's broaden out to the grandest scale, cosmology. How does GR describe the universe?
Applying GR to the whole universe led Einstein initially to add the cosmological term, lambda g mu nu, to his equations.
Why?
He wanted static solutions, a universe not expanding or contracting, even with matter. The source discusses a spherical static solution with this lambda term, which modifies the metric, adding an r-squared term.
Does lambda affect orbits?
Subtly, yes, on perihelion motion, and some solutions with lambda have impassable barriers where a metric component goes to zero.
The text also mentions an isotropic solution for multiple static particles in weak fields. What does that tell us?
In the weak field, low velocity limit, the metric for multiple particles simplifies, depending on the sum of their Newtonian potentials, omega. It ignores complex field interactions.
And for continuous matter.
Extending that, in the weak field limit, Einstein's equations relate parts of the Ricci tensor to matter density rho, resembling Newton's Poisson equation. The energy-momentum tensor T mu nu is introduced, T44 is density, and the Einstein tensor G mu nu is related to T mu nu.
But limitations.
Yes. The source warns this weak field approximation breaks down, especially with multiple interacting bodies, where the forces needed for static balance contribute their own gravity.
So applying GR cosmologically brings new possibilities, new complexities compared to Newton. After all this theory, what's the role of experiment? How well justified is GR by evidence?
The source makes a good point about levels of experimental verification. There's simple verification, theory matches data; suggestion, data hints at new ideas; and compulsion, data forces adoption of one theory.
And compulsion is hard.
Very. Hard to make rigorous, unambiguous inferences just from data. For example, for a single particle's gravity field, even assuming relativity's basics, what can experiment really pin down about the exact metric form? We assume spherical symmetry, static field, seems justified. But proving the exact function solely from experiment is tough.
It highlights that constant back and forth between theory and experiment in science. Now, more math. Invariance and tensor densities. Why are these important?
Invariants don't change value under coordinate transformations. Tensor densities transform like tensors, but pick up an extra factor related to the Jacobian, how volume scales.
Why useful?
They let us build laws and quantities truly independent of coordinates. The source mentions the generalized Kronecker delta, epsilon mu nu sigma tau. Then the determinant of the metric tensor, g. Square root of minus g turns out to be a relative scalar of weight 1. It gets multiplied by the Jacobian when you change coordinates. This leads to the invariant volume element, root minus g tau. Surface and 4D volume elements can also be tensors. Tensor densities are key because integrating them often gives invariants, which form the basis for action principles in physics.
Okay. Shifting slightly, rotating frames of reference, how does GR handle non-inertial frames?
Moving to a rotating frame makes the metric tensor more complex. It reflects the fictitious forces, centrifugal and Coriolis in that frame.
Example.
A rotating disk. The source calculates how particle density measured on the disk, proper density sigma, relates to density sigma prime seen from a fixed inertial frame.
And then the result.
Due to Lorentz contraction and time dilation combined, the fixed observer sees a higher density. Sigma prime equals sigma divided by root 1 omega squared r squared c squared. Shows how even density becomes observer-dependent in non-inertial frames.
Now, crucial concepts, the divergence and conservation laws in GR's tensor language. How do they generalize from 3D calculus?
Divergence, the outflow idea, is generalized using covariant derivatives for tensor fields in 4D spacetime. Formulas exist for vectors, tensors. A truly fundamental theorem is that the divergence of a specific tensor, g nu mu minus half g nu mu, related to the Einstein tensor, is identically zero.
Why is zero divergence significant?
In physics, it often signals a conservation law. Vanishing divergence of current implies charge conservation. So finding a world tensor whose divergence is always zero suggests something fundamental is conserved.
And this connects to the law of gravitation with matter, the energy momentum tensor T mu nu.
Exactly. By identifying that conserved tensor, g nu mu minus half g nu mu g, as being proportional to the energy momentum tensor T nu mu, we get Einstein's full field equations with matter. G mu nu minus half G nu G equals minus 8 PAG over C fourth T mu nu.
The cornerstone equation, curvature equals matter energy.
Precisely. Linking space-time geometry, left side, to matter energy distribution, right side. The source mentions the stress energy tensor for a perfect fluid, and how its local conservation, divergence of T is zero using covariant derivatives, gives the equations of hydrodynamics. The key is the principle of identification, matching abstract math quantities from the metric with physical concepts like mass, momentum, stress.
A powerful synthesis. Gravity isn't external, it's intertwined with matter via geometry. The source mentions energy momentum conservation with forces, using an abstract Galilean geometry.
Yeah, if we use coordinates misaligned with the true curved geometry, we might invent forces to explain deviations, imposing a flat Galilean view on curved reality,
Leading to confusion.
potentially confusing coordinate mesh units with true physical volume. In this view, local conservation of the supposed energy tensor is divergence of T equals zero. But when real forces act, the hydrodynamic equations get modified with terms involving the metric and T mu nu. Components of T are identified with momentum energy density, and a body force emerges related to metric derivatives and T.
The geodesic motion of a particle also comes up, linked to least action and invariant mass.
Yes, an elegant result. A free particle, only gravity acting, follows a geodesic, the shortest path in curved spacetime. Derivable from the principle of least action, related to maximizing proper time along the path, the particle's invariant mass stays constant. Symmetrical properties mean no preferred direction to deviate.
So particle motion is dictated by geometry. Now, gravitational waves, a huge prediction, now confirmed.
The source looks at this by linearizing the metric. G nu is flat Minkowski metric plus a small perturbation hu mu nu.
Plugging that into Einstein's equation.
Yes. And using a specific coordinate choice, gauge condition, simplifies things. You end up with a wave equation for the perturbation hu mu nu.
Showing what?
Showing these disturbances in curvature propagate at speed c. Predicting gravitational waves ripples in spacetime, the theory also implies gravitational mass equals inertial mass.
LIGO Virgo's detections were monumental confirmation. Now, the Lagrangian formulation of gravity. Benefits.
It's an alternative, equivalent way to get the field equations. The gravitational action integral uses the scalar curvature, g. Applying least action, varying this integral regarding the metric, setting variation to zero derives Einstein's equations.
Useful for
Certain theoretical work, like quantum gravity attempts or exploring modified theories. Also, varying the matter Lagrangian regarding the metric directly gives the energy momentum tensor, linking matter and curvature.
Finally, before more speculative stuff, the perplexing pseudo-energy tensor of the gravitational field sounds contradictory.
It arises from wanting a local conservation law for energy momentum that includes gravity's energy itself. GR implies global conservation, matter plus field, but defining a local tensorial energy density for gravity is tricky.
Why?
The source mentions a quantity S nu mu related to gravity's contribution. Contrasts GR's approach, keep laws tensorial, find global conservation, with classical physics, modify quantities like potential energy for local conservation. The pseudotensor T nu mu sometimes used isn't a true tensor. Its value depends on coordinates. You can make it zero at any point by choice. So it's not seen as fundamental localized energy density in GR's covariant framework. Though a tensor density T nu mu, including all energy, plays a role. Hamiltonian derivatives and least action help understand dynamics here.
It highlights a deep conceptual difference in localizing gravitational energy. The text briefly mentions alternative gravity theories. What directions?
Exploring variations of the gravitational action. Example, while action, using g mu nu instead of just scalar g.
Do Einstein solutions work there?
Vacuum solutions, g mu nu equals 0, 0, often satisfy these alternatives too, but alternative theories often give higher-order equations, needing more boundary conditions, possibly allowing unrealistic solutions. Einstein's theory remains dominant due to success and relative simplicity.
Okay, let's dive into the profound geometrical interpretation, gravity as curvature of space-time. How is this understood mathematically?
Riemannian geometry is the framework. The metric g mu nu, 10 independent components in 4D, defines the geometry. One way to visualize is embedding this 4D curved manifold in higher dimensional flat space. Turns out, you need at least 10 Euclidean dimensions.
Wow.
Curvature is described by things like principal radii of curvature, related to the Ricci tensor, g mu nu, and scalar curvature, g. A simplified 5D example is given relating g to these radii.
The text mentions a radius of spherical curvature as an invariant property. What's that?
A property of the curved spacetime itself, independent of coordinates. Einstein's equations for empty space with cosmological constant lambda, g mu nu minus half g mu nu, g mu nu lambda, g mu nu, can be interpreted geometrically as spacetime where the quadric of curvature is a sphere at every point. Same curvature radius in all directions related to lambda. This radius is always relative to our material standards of length.
The text also speculates about alternative laws if material units adjusted to other lengths.
Yes, and justifies assuming symmetry for a particle's field by arguing symmetry is relative and the particle is the standard, linked to light propagation symmetry, ds0.
This geometrical view is profound. Gravity as warped fabric. The source then discusses specific cosmological models, starting with spherical space.
A universe with 3D space having constant positive curvature, visualized as the surface of a 4D sphere, finite volume but unbounded, no edge, no center.
Like the surface of the Earth, but one dimension up.
Exactly. The source gives the metric for this 3D sphere, then generalizes to a 4D spherical surface and 5D Euclidean space related to de Sitter's model. Coordinate changes can give a time coordinate.
What are unusual properties of de Sitter's spherical universe?
One is that light speed isn't constant, depends on distance. Intriguingly, atomic vibrations would slow down over time, causing redshift from distant objects, not Doppler, but time itself changing rate.
Wow. Geometry affecting time flow.
Yes. And spherical geometry can mislead about distance. Antipodal points might seem far via one path, but closer via another. Our flat space intuition breaks down.
The text contrasts Einstein's static spherical world with de Sitter's empty world. Key differences.
Einstein's model, early, had uniform matter and positive lambda to balance gravity for a static, finite universe. De Sitter's had lambda, but no matter. Surprisingly, it could still expand in some coordinates.
Were they compatible?
Source says Einstein's empty space equations, without lambda, aren't consistent with de Sitter's g mu nu, Gell's lambda g mu nu form. If the universe had that form, it implies an energy-momentum tensor, but its distribution is indeterminate.
What about observations back then?
Slow star speeds in our galaxy, but high recession speeds of nebulae, other galaxies, hinted at non-static universe, raising questions about curvature. Einstein's model is stable, particle stays put. De Sitter's tended to scatter particles. De Sitter redshift was a possible explanation for receding nebulae.
Singularities.
De Sitter's metric had one at a certain radius, maybe a mass horizon, but coordinate singularities can be tricky. Finding globally regular coordinates for a finite universe was noted as difficult.
These early models, though outdated now, were foundational for applying GR to the cosmos. Now, how does electromagnetism fit into GR?
Maxwell's equations for flat space need generalizing for curved spacetime. Replace ordinary derivatives with covariant ones. Consider how fields interact with curvature. Key objects. Electromagnetic field tensor F mu nu combines E and B fields, and 4 current G mu, charge current density.
So curvature affects electromagnetism too?
Yes. EM, potential force propagation speed, isn't generally constant or isotropic in curved space, but light rays themselves still follow null geodesics, ds squared equals 0 in any geometry. The source mentions formulating retarded potentials in curved spacetime too.
What about electron self-energy and electromagnetic mass? How does relativity complicate that?
The idea that electron mass might be purely electromagnetic runs into paradoxes regarding invariant versus relative mass. Some analyses suggest invariant mass can't be solely EM field energy. Others link relativistic mass increase to it. Source hints maybe the split between Maxwellian and non-Maxwellian stresses is artificial, needing a unified theory. A key challenge, explaining why invariant and relative mass are equal for a stationary electron.
Okay, let's get speculative with Weyl's unified field theory. What was his core idea?
Weyl's theory, post-GR, tried to unify gravity and electromagnetism geometrically. Central idea. Introduce a gauge factor for length. Length might change not just from curvature, but from its path via parallel displacement.
So length itself becomes path-dependent, more relative than in GR.
Exactly. Length transfer becomes non-integrable. Weyl modified parallel displacement by adding a new vector field, kappa mu, the gauge vector.
How did this unify forces?
Length now depended on the path integral of kappa mu. To keep consistency under local length rescaling, gauge transformations, he introduced intensors, in invariance, and incovariant derivative. By modifying the Ricci tensor scalar curvature with kappa mu, he aimed for a theory where gravity, curvature, and electromagnetism gauge vector kappa mu.
But alternatives?
Source contrasts this with maybe length is unambiguously comparable, Einstein's view, and Weyl's geometry is more abstract.
The source then discusses an even more generalized theory of parallel displacement. Starting point.
Consider the most general continuous formula for vector change under parallel displacement, using arbitrary coefficients, gamma mu nu alpha, not assumed tensorial.
What comes out of that?
Parallel displacement around a tiny loop yields a third-rank tensor, star b mu epsilon nu sigma, generalizing the Riemann tensor. Contracting it gives other tensors like star g mu nu. A Lagrangian and variational principle can be formed. Key idea. A natural gauge of the world from matter-like properties. It explores identifying a geometric tensor R mu nu with the metric g mu nu based on comparability of proximate relations.
Sounds incredibly abstract. 4-point elements, affine geometry.
Yes, maybe fundamental units involve relations between 4 points. Affine geometry, parallels, no metric needed, might describe displacement equivalence. The full star B tensor might relate to electron structure. Star G mu nu extracts the gold from this complex structure. Lagrangian involves star G mu nu and EM field. Energy tensor from Hamiltonian derivatives. Generalized volume is fundamental invariant. Regauging links a tensor P mu nu to material energy tensor.
Wow. Deepest levels, trying to unify everything. Okay, wrapping up this incredible journey through relativity, what are the main takeaways?
We saw how Einstein's gravity law emerges from geometry, linked to mass energy. Symmetrical particle properties arise from their role as standards. GR accounts for Newton, but adds crucial refinements. Mercury's perihelion, light deflection, verified experimentally. We touched on later ideas. Harwood's identities, Eisenhart-Veblen leading to Weyl, contrasting Einstein's metrical frame versus Weyl's track framework, may be unified by the generalized theory.
So this deep dive covered a huge landscape, from the nature of measurement itself to cosmology to speculative unified theories. Relativity clearly revolutionized our understanding, showing deep connections between space, time, gravity, even observation.
Indeed. We saw how fundamental quantities can seem manufactured by measurement, how forces might be geometry, raises really surprising, profound questions about reality itself.
Absolutely. For you listening, if your curiosity is sparked, there's so much more. Dig into the experiments, Michelson-Morley, Fizzo, explore tensor math, or the ongoing quest for unified theories, building on Weyl and beyond. It's a rich field.
And maybe one final provocative thought. How much does our reliance on measurement, our inherent observer perspective, shape our understanding? Is reality as we perceive it intrinsic, absolute? Or is it somehow a product of how we interact with it, how we describe it? A question still driving science.
A truly powerful question to ponder. Thanks so much for joining us on this exploration into the mathematical heart of relativity. Until our next deep dive, keep questioning, keep exploring the incredible universe around us.